Now, remember this formula of r, which we wrote as summation small xy divided by root under summation x square, small x square, and summation y square, can be written in various different forms by doing a bit of algebraic manipulation. So basically this is x minus x bar into y minus y bar in the numerator divided by summation of x minus x bar square into summation y minus y bar square. Now from this you can actually derive, if you do a little bit of mathematical manipulation, you can actually arrive at another useful formula for the same Carl-Pearson's correlation of coefficient, which is n times sigma xy minus sigma x into sigma y, and under the square root you have n times sigma x square minus sigma x whole square. Similarly, under the second root you have n times sigma y square minus sigma y the whole square. Okay, now I know this formula doesn't look as pretty as you'd probably like it to be, but it has an advantage. You don't need to calculate the mean value of x and y and then calculate deviations. If you notice, you just need x, y, x square, capital X, y square, and capital X into y. So calculations can become simpler even though the formula looks a little bit more bigger. If you are just given a data as we showed in the example, you can use whichever method you're comfortable with, whichever formula you're comfortable with. But for purpose of short questions or maybe some multiple choice questions, you may be required to remember both the versions of the formula. Just to show you why the formula that we just discussed is more useful, remember this is the formula. So you have x, y. The additional columns that you will need to calculate are, you will need to calculate x square, you will need to calculate y square, and x into y. So use your calculator and find x square and y square. So here you have the completed table. Summation x is 240, summation y is 200, summation x square is 7332, summation y square is 5122, and summation xy is 6104. We put that into the formula given and we get the same answer, 0.8195 as the correlation coefficient, Carl-Pearson's correlation coefficient. When I was solving this sum, I realized that since we have very big numbers, similar to our earlier case of arithmetic mean and standard deviation, the shortcut method can be utilized. Even the book discusses the shortcut method. So based on that, instead of n times summation xy, it is summation dx dy minus summation dx into summation dy divided by under the root n times summation dx whole square minus summation dx square, and here we have n times summation dy square minus summation dy whole square, where dx is x minus an assumed mean a. Always choose one of the central numbers as a, and dy is y minus the central value of b. So a and capital B are our assumed means. They can be any arbitrary number. Ideally, choose one of the middle numbers from the data of x and y that you have with you. Okay. The last point, another point that I want to discuss about is the assumptions about the Karl Pearson's coefficient. There are three main assumptions. The first is that the nature of the association between the two variables under study is a linear one. So remember, that's why I said the Karl Pearson's correlation coefficient measures the degree of linear association. It is also based on the assumption of normality of the two variables, that is, both the variables exhibit normal distribution properties. It is generally used when you are suspecting a causal relationship between the two, cause and effect relationship between the two variables under study, and that there has been proper grouping of the variables has been done. And finally, the error of measurement. The error of measurement basically gives you a value which can be added and subtracted from the R or correlation coefficient that you have calculated for the sample that you have in hand. It basically refers to gives you the limits within which the correlation coefficient will lie if you calculate it for different samples coming from the same population. Okay. The probable error of this R is given by a formula 0.6745 times 1 minus R square by n, where R is your Karl Pearson's coefficient, n is the number of pairs of observations that you have. Okay, 0.6745 is a constant. Okay, probable error of R. Once again, just understand the concept. I don't know how important this formula is. Basically, you have with you one sample which has been taken from some population. You have calculated its Karl Pearson's coefficient. Now, if you add and subtract this probable error, you will get an upper limit and lower limit, within which, so basically your upper limit is R plus the probable error of R, and your lower limit is R minus the probable error of R. If you take repeated samples of data with the same number of observations from the same population and calculate the Karl Pearson's coefficient for these repeated samples, all the values of R will lie within this range. It is a statistical concept and slightly technical concept. Another statistical concept related to the Karl Pearson's correlation coefficient R is the coefficient of determination, which is basically r square. Find the Karl-Pearson's correlation of coefficient, square it, and you have got the coefficient of determination. The coefficient of determination basically is the ratio of explained variance to the total variance. Again, this concept will make more sense to you when we discuss regression analysis. In regression analysis, we say that the variable y is being explained by variations in variable x. So r square, or the coefficient of determination, gives us an idea about how much of the variations in the variable y, or the dependent variable, remember this is called, when you express y as a function of x, y is called your dependent variable and x is called the independent variable. In regression analysis, the idea is that changes in the value of x will result in changes in the value of y. So the coefficient of determination actually becomes important in the context of regression analysis. It will tell you, or it will give you an idea as to how much of the variations in the dependent variable can be explained by variations or changes in the x variable. So it gives us an idea about the explanatory power of x, or the x variable, or the independent variable. I won't go into more detail than this because I don't think you need it at the moment.